the last lecture, we were talking about the Wiener process. And many of its features and properties that were useful for understanding Brownian motion. We talked about things like the Markov property, how to simulate it, how to incorporate drift, and things of that nature. So in this lecture, we're going to talk about the important process of arriving at the receiver. So if you think about what happens in a molecular communication system, we have a transmitter over here and a receiver over here. Now I deliberately drew the transmitter very small. Normally what we assume is that the transmitter is invisible to the propagating molecule. So for instance, if there's a molecule here, the transmitter will release it, and then we'll assume that the transmitter plays no role in modifying the molecule's movement. So what we're talking about here is Brownian motion. And the idea is what happens after some random walk? What happens, or what is the process by which the molecule, the signal bearing molecule, arrives at the receiver? What is the process by which the signal bearing molecule arrives at the receiver? So if Brownian motion is all about propagation, then that propagation has to terminate. I mean, in traditional wireless communication, it terminates, the signal terminates at an antenna. Here, we're just going to say it terminates at the receiver. Let's define the receiver as a connected region. I'm going to call it script R, like so. So the receiver consists of a set of points, script R, and the signal bearing molecule arrives at the receiver when its Brownian motion, B of t, is inside that region R. So there's two things that can happen when the molecule arrives. One is that the molecule is absorbed, and that's called an absorbing receiver. In an absorbing receiver, the molecule's Brownian motion is terminated when it arrives. On non-absorbing receiver, what we're going to assume is that the molecule enters R and continues propagating. So to visualize the difference, we have a molecule that is propagating by Brownian motion, an absorbing receiver, for an absorbing receiver, the molecule arrives at the region R, This is the region R. It arrives at the region R and stays there. That's it. So its motion ends as soon as it arrives at the receiver. For a non-absorbing receiver, the random motion continues within the volume. So this is for a non-absorbing receiver. Now, these aren't the only two possibilities. You could imagine a non-absorbing receiver where this motion, where in other words, R was solid. So in other words, it would encounter the receiver and then maybe come back later. That kind of receiver is more difficult to model than either of the two examples that I'm presenting here. But just bear in mind that these aren't the only two possibilities. Okay, so let's talk a bit about absorbing receivers first. So bearing in mind that the receiver does not interact with the propagating molecule before it arrives, the most important thing about the Brownian motion in this case is the time of arrival. So once it has arrived, bearing in mind the Markov property, once the molecule arrives, so by the Markov property, once the molecule arrives, we know B of t. So in other words, we know where the boundary is. We know that the molecule has encountered the actually, let's call this time of arrival TA. So we know B of TA, we know where the boundary is, we know that it arrived at time TA, so we know its exact position at time TA. So therefore, by the Markov property, we don't, this is sufficient. This is sufficient to characterize its past. So in other words, all we need to know is TA and the fact that it arrived. What this implies is that, and also the fact that it's absorbed, this means it only arrives once. So because it's absorbed, it only arrives once. What we're interested in here is the first arrival time distribution. So just to be 100% clear about this, only arrives once. What do I mean? Well, if we go back to the previous page, this guy comes along and arrives here, then it's stuck, it's absorbed, so it doesn't come back. I don't have to worry about it coming back. So it only arrives once, which means I only care about the first arrival time. If I know the first arrival time, then by the Markov property, we know everything we need to know about its past because we know its time and position. So it's the first arrival time distribution that's important here. In other words, that's the first time the receiver sees the molecule, and that contains all the information. That knowledge contains all the information the receiver needs to know. So define I'm going to call it capital T as the first arrival time. Then capital T is equal to the minimum of I mean, okay, so notionally you can imagine that the Brownian motion could continue after arrival. I mean, it's we assume that it's absorbed so that the motion is terminated. So this is still notionally true, but you can also imagine it continuing. It'll be the minimum of the set, oops, the set of times such that the Brownian motion is inside the receiver. So in other words, this is the set of times where the Brownian motion is inside the receiver. Notionally, it can continue past the boundary or not. We assume that it terminates, so this is valid either way. But if this is the set of times where the Brownian motion is inside the receiver, the first arrival time is just the minimum of those. In one dimension, which is what we're talking about here, actually, let's continue that discussion on the next page. In one dimension, we have the following setup. So here's my one-dimensional line. Here's my absorbing receiver in one dimension. Here is the release point for molecules. I will always assume that is at, so this is X here. I will assume that's at location X equals 0. In other words, the origin. And I'm going to assume that this is at location X equals D, where D is greater than 0. So in other words, the distance here is D. So in one dimension, we can set up the first arrival time T as the minimum time of the set of times where the Brownian motion is greater than or equal to D. Oh, I said X here, but this is equivalent to B of T. B of T is measured on the X-axis here in one dimension. There are some standard ways to calculate first arrival time distribution in one dimension. There are actually not very many closed form ways to do this. It turns out to be a complicated problem in general, but the drift-free case is actually pretty easy to formulate, and there's a neat little trick to it. So we're going to go through the derivation. So one-dimensional first arrival time distribution. So basically what we're going to do is we're going to set this up in terms of the cumulative distribution function. So, I mean, you know what the PDF is, the probability density function. So what we really want is the PDF. So that's F of T. The CDF will be the probability that T is less than some little t, some variable here. So the notation here is that T is my first arrival time as a random variable, and little t is just some constant that comes along here, some arbitrary constant. So if you pick little t, this is just the probability that my first arrival time is less than that arbitrarily chosen little t. Now here's how it's going to work. Consider the following probability. What's the probability that if I give you some t, that the first arrival time is less than t, and the position of the Brownian motion is greater than the position of the boundary, D. Okay, so again, notionally, let me just give you an aside here. The absorbing Brownian motion, it terminates at the boundary. But here, I mean, there's no reason mathematically why we can't just allow it to continue. So this will be a Brownian motion that continues after the absorption time. So what's the probability that the first arrival occurred at a time less than little t, and the Brownian motion is beyond the boundary? So the setup looks like this. So here's D, B of t is somewhere over here, and t is greater than, excuse me, yeah, t is the time at which the Brownian motion is over here is greater than the first arrival time. Well, that's obvious, because if you went through this boundary, then the first arrival time must have happened earlier. So for that, we're going to express this two ways. One is, by Bayes' rule, I can break this up two ways. I can say the probability t is less than t, given that b of t is greater than d, times the probability that b of t is greater than d. The other way to do this is the opposite. So it's the probability that b of t is greater than d, given t is less than t, times the probability that t is less than t. Okay, so first off, look at this. What is the probability that the first arrival time is less than t, given that I'm past the boundary? Well, I just said that. I must have arrived at the boundary at some earlier time. If the Brownian motion is continuous, which it is, I must have arrived here at some earlier time in order to go past it. So I'm assuming that I went past it. So I must have arrived at some earlier time. So that means this is 1. Now this one, I'm going to hand wave a little bit. So basically, the question here is, if my first arrival time is less than t, then what's the probability that I end up on this side? In other words, the Brownian motion ends up over here as opposed to on this side. So I'm going to hand wave a little bit. This is a Brownian motion without drift. I can go either way. I know that at time capital T, I must have been here. So what's the probability that I end up on the positive side as opposed to the negative side? You can do this rigorously. There's more rigorous ways to derive this, but because this is a Brownian motion without drift, if I know that I'm here, it's a zero mean. So you can imagine the Gaussian distribution like so, and it's 50% that I'm on this side as opposed to this side. So I'm going to hand wave and say this is 1/2. Now notice that by Bayes' rule, these two are equal to each other. So this implies the probability that b of t is greater than d is 1/2 the CDF of the first arrival time. So that is super helpful, because what we can do now is we can say, okay, what is this? What's the probability that my Brownian motion is beyond the boundary? You can set that up. We know that b of t is distributed Gaussian with zero mean and variance 2dt. Actually, let's make this less complicated. So the fundamental variance of the Wiener process, let's just call it sigma squared. So b at t is distributed normal with mean 0 and variance sigma squared t. So this means the probability that b of t is greater than d is equal to the integral from the boundary to infinity of 1 over root 2 pi sigma squared t, e to the minus my position, I'm going to call it b of t squared divided by root 2 pi sig. Sorry, that's not right. In the denominator, I just have the variance, which is 2 sigma squared t, twice the variance, which is 2 sigma squared t, dB of t. Now, you should know that this is basically the error function complementary. So I'm integrating from d to infinity of a Gaussian random variable. And without exactly specifying, you can get this on your own without exactly specifying what this is. This is 1/2, or how to get this, excuse me, 1/2 the error function complementary of d over root 2 sigma squared t. This can also be written because ERF C is 1 minus ERF D over root 2 sigma squared t. So that's pretty cool. We know that, we then know that from the previous page. Sorry, there we go. From the previous page, we know that probability of B of t is greater than D is equal to 1/2 of the CDF of the thing we're looking for. So coming back here, this implies that P of t less than some value little t is equal to twice this, which is just 1 minus ERF D over root 2 sigma squared t. Finally, to get what we want, which is the first arrival time PDF, this is just d by dt of probability t less than t. That's just by basic probability. You integrate to get the CDF, which means you differentiate to get back. And this is straightforward. You can do it yourself. What you end up with is d over root 2 pi sigma squared t cubed e to the minus d squared over 2 sigma squared t. There it is. So that is the first arrival time distribution. Without drift. This has a special name. Actually, it has a number of special names, but the name that I usually hear it called the Levy distribution. And it is often rewritten kind of like this, C over root 2 pi t cubed e to the minus c squared over 2t, where c in this case would be equal to d over sigma, or c squared, I guess, is d squared over sigma squared. If you're doing Brownian motion, sigma squared is 2 times the diffusion coefficient, so that's d squared over 2d, like so. And this is called the scale parameter. So this is the first arrival time distribution. in terms of the fundamental physical components, distance and diffusion coefficient. Just want to point something out about this distribution, which is that first off, it's only defined, a few facts about this, only defined, oops, for t greater than 0. Another thing is it's a very heavy tail distribution that decays on the order of 1 over t to the 3 halves. Now, this might seem funny. You might look at this and think, okay, it came from Gaussian, so it must have an exponentially decaying tail. But no, if you look here, t is in the denominator. So as t goes to infinity here, this becomes e to the 0, which is 1. And this is the term that dominates. So as t gets very large, this is the term that you have left. Also consider, what is the mean of this distribution? The mean of this distribution, if you multiply this by t, what do you get? You get c over root 2 pi t. So this is 1 over root t in the denominator. You can ignore this part because as t becomes large, this will decay. And if you integrate this from 0 to infinity, if you integrate this times t, so in other words, you're integrating 1 over root t from 0 to infinity, you actually get infinity. So the mean of this distribution is infinite. So in other words, the average first arrival time with drift, or without drift, excuse me, is the expected value of t, which is infinity. You could end up waiting a very long time. It will arrive, the particle will arrive eventually with probability 1. If you integrate this distribution from 0 to infinity, you get 1, so it will always arrive, but your expected waiting time is actually infinite. When there's drift, the story changes a little bit. I won't derive this. You get a different first arrival time distribution, which is called the inverse Gaussian distribution. So we again have our physical parameters d, the distance between transmitter and receiver, capital D, the diffusion coefficient, and v, the drift velocity. But we're going to form them into two compound parameters called lambda, which is d squared over 2d. So that's much similar to the scale parameter we had in the Levy distribution. And mu, which is d over v. And then we have the inverse Gaussian distribution. Sorry, I should point this out with drift v greater than 0. So positive drift from the transmitter to the receiver. Now the first arrival time distribution is given by root lambda over 2 pi t cubed, which is what we had before. Exp. By exp, I mean e to the power of, except this is going to be big and annoying, so it's easier to functionalize it rather than put everything in the exponent. Lambda of t minus mu squared divided by 2 mu squared t. Now, if you look at this a little more closely, a couple things pop out. First off, in the exponent, I have a t squared term up here, capital T squared term up here, and a single t in the denominator. So as t becomes large, this will grow, not counting the minus, this will grow on the order of t. So this thing will end up being e to the minus t, which overwhelms the 1 over t cubed that we have or excuse me, 1 over t to the 3 halves that we have out here. So this is an exponentially decaying tail. In this case, mu is the mean arrival time. And that actually makes sense. If you look here, this is the amount of time it takes to travel distance d at velocity v, and that turns out to be the mean arrival time, which is less than infinity. Moreover, if v goes to 0, then this mu goes to infinity, and I suppose you could take the limit as mu goes to infinity over here, and hopefully you would get back to something like the Levy distribution. This is also called the walled distribution. I've seen that term as well. So the inverse Gaussian or walled distribution. Okay, so in the next class, we'll talk a bit about absorbing receivers.